Thanks, Cynthia, and thanks for that wonderful introduction, and thank you all for being here. And my talk will be about composition, which Cynthia just told us a little bit about, and my hope is it will delve a lot deeper into composition, understand why it's important, and also understand that it's a subtle, deep area of study within the differential privacy literature. We've made a lot of progress in understanding composition, but we also have a lot of challenges and open questions that we're still trying to understand. So as we learned from Cynthia's introduction, differential privacy is, I would say, Cynthia didn't say it, but I can say it because I didn't invent differential privacy, differential privacy is revolutionary in the study of privacy-preserving data analysis, and there are at least two main properties that it has that none of the other rigorous ways of thinking about or studying privacy-preserving data analysis have. One is what Cynthia referred to as being future-proof, providing privacy even in the context of additional information, auxiliary information that an adversary might have. And the other one, which will be the focus of my talk, is composition, which says that even when we run multiple analyses, each of which is differentially private in isolation, when we run them all together, when we release the results of all the analyses together, privacy is still maintained up to some smooth, gradual degradation. As Cynthia said, the epsilons can add up. We'll see that we can say much more than that. There is some degradation under composition, but we can still reason about and analyze what happens. And I want to briefly contrast this with two of the approaches, of the alternate approaches that Cynthia touched on. So if we talk about just releasing statistics, there's a very simple example that shows you that that doesn't compose. Even if you're doing statistics over a big population and all you're releasing are aggregate counts, think about releasing the number of faculty members in a university that have heart disease. It's a big university, so that doesn't seem problematic. But then you also release the number of faculty who have heart disease who are not the president. It's another big collection of people. Each of these answers on its own seems to be somewhat privacy protective, but given these two answers, you can subtract the second from the first, and you've just learned that the university president has heart disease. We have a serious privacy violation. So composition is subtle. Pieces of information flow together in unexpected ways, and we want to understand it. Also, if you de-identify data sets, that isn't robust to composition. I won't talk about that. So composition is a core issue in the study of privacy-preserving data analysis, core issue in understanding differential privacy, both because it's unavoidable. Okay? In reality, there are multiple analyses. Okay? No one collects a database of sensitive, valuable information and then just runs one analysis on it. That doesn't happen. Even if it did happen, our data are in different data sets. They're subject, even if each data set is only subject to one analysis, our data are in multiple analyses. So we just can't get around having to reason about composition. And as Cynthia said, composition is what makes differential privacy programmable. As computer scientists, we understand how important that is. We can take algorithms or subroutines, put them together in innovative ways, and get interesting differentially private algorithms. So composition is important, and we want to understand it. And the first question is, how exactly do we define composition? And the way I want to define it, was sort of informally defined before this, but we defined it formally in work with Cynthia and Salil Vadhan, where what we wanted to do is we wanted to handle composition even when the adversary can be adaptive, so the adversary can choose what differentially private algorithms we run, and even when the adversary is in control of the data sets. Okay? So the way we formalize this, being good cryptographers that we are, is as a game, where we have the adversary. The adversary basically wants to learn as much as it can from an adaptively chosen collection of differentially private analyses. So it chooses the analyses one by one. It specifies a differentially private algorithm or mechanism, M1, that's going to run, and two adjacent data sets, X10 and X11. These are the data sets that only differ in one person's information, say only in my own information. So the adversary specifies the data set, specifies the analysis, and then we decide either we run the analysis on the left data set or on the right data set. Think about it as if the left data set has my information in it, the right data set, my information is replaced with complete junk, or I'm not in the data set. Okay, so one of these is run, either the left or the right. We give the adversary the answer, then it chooses a second algorithm and a second pair of data sets. This goes on for k rounds. That's k-fold adaptive composition. And the adversary gets to see all of the answers either on the left data sets or on the right data sets. And what we require is that even with all of these k answers that the adversary saw, even though it could adaptively specify the algorithms that were being run and the data sets up to my information that they were run on, still it can't tell, it isn't learning much about my data, and in particular its entire view should be differentially private. Any event that can happen to me, given its entire view when the algorithms run on my data, can happen with about the same probability if I was never in any of the data sets at all. That's a strong property, and that's a strong composition guarantee, and differential privacy actually gives us this type of strong resilience to composition, or strong composition. So that's what I want to tell you about today, and the way I want to start it is by telling you about basic composition, where the epsilons add up, just giving you an idea of some basic properties of differential privacy under composition. Then we'll go and see advanced composition, what more we can say. That's work from now, I guess, 6 years ago. But then in the last year or two, there's been a lot of further activity giving us an even more refined understanding of composition. And my hope is to take us all the way to these most recent works in the talk. So basic composition tells us that if we take k algorithms, each of which is, say, epsilon 0 differentially private on its own, running all of them together, the epsilons just add up. We still have k times epsilon 0 differential privacy. Remember, throughout this, think of epsilon 0 of epsilons as either a small constant. You might even think of it as something like 1 over k, if we know in advance what k is. So even this k times epsilon 0 can still be a very small quantity. We still have strong differential privacy. And I'll briefly tell you about how we can use that. Already that is something that lets us answer multiple adaptive queries on a data set. So I won't do many proofs in the talk today, but this is one that I do want to linger on. How do we show that basic composition holds? So we have two algorithms. A1, the first algorithm that's going to run, when we run it on a data set, we have a guarantee that that's epsilon 1 differentially private. And then we have an adaptive second algorithm. The second algorithm also runs on the data set, but it also sees the output of the first algorithm, Z1. So it runs on data set and the output of the first algorithm. And our guarantee is that whatever the first algorithm output, this second algorithm is epsilon 2 differentially private in its use of the data, in its access to the data set. Then the claim is that if we run both of these together, so we run the first algorithm, we publish its output, and then we run the second algorithm on the data set and that output, taken all together, we still get epsilon 1 plus epsilon 2 differential privacy. The epsilons are just adding up. And it's a proof sort of follows from the definition of differential privacy. So we know that for any two adjacent data sets, D and D prime, and for any two events that can happen, for any two possible outputs, Z1 and Z2, we know from differential privacy of the first algorithm that the probability of the output, call this P of Z1, the probability of the output Z1 when I run the algorithm on the data set D, the ratio between that and the probability of the output Z1 when I run the algorithm on the database D prime, these are about the same. The ratio between them is bounded between e to the minus epsilon 1, that's sort of 1 minus epsilon 1, and e to the epsilon 1, which is 1 plus epsilon 1. So these ratios are very close to 1. Similarly, for the second algorithm, because it's differentially private, we know that the ratio of these two probabilities, the probability of the output Z2 when we run on the real data set D, and the probability when we run on the adjacent data set are about the same. They're bounded between e to the minus epsilon 2 and e to the epsilon 2. And when we look at the probability of these two outputs coming out together, the algorithms are being run using independent coins, and that's always important in composition. We have independent runs of the two algorithms. So the probability of the two outputs is just a product of the two probabilities, and we get the ratio that we want. The probability of the two outputs on the data set D and D prime, the ratio between them is between e to the minus epsilon 1 plus epsilon 2 and e to the epsilon 1 plus epsilon 2. Our new global epsilon is just epsilon 1 plus epsilon 2. So it follows simply, and that gives us our basic composition guarantees. Already that gives us quite a lot. So we can use that to answer multiple adaptively chosen queries on a data set. I won't linger too much on this. Kunal will tell us more about algorithms. I will just say briefly that we know how to answer a single statistical query on a data set from the work of Dwork et al. The way we do it, given a query, we just add some noise to it. The noise is drawn from a Laplace distribution scaled to our privacy parameter. So the smaller the privacy guarantee we want, the larger the noise we add. And that gives us differential privacy, so long as the query has sensitivity 1, so long as its value can't be affected too much by any individual. Now, answering, of course, once we've collected a database of sensitive information, we want to do much more than answer a single statistical query. And composition already tells us that we can answer multiple queries. So if we want to answer k queries, even k adaptively chosen queries, each of which, again, has sensitivity 1, can't be affected too much by any one individual, all we need to do is add independent Laplace noise to each of the queries. The more queries we want to answer, the more noise we need to add. So the noise scales as k over epsilon. For each of the queries, since we're adding noise k over epsilon, we have epsilon over k differential privacy for each of them. And since we're answering k all together, the epsilon sum up, and we get epsilon differential privacy for all k of the answers together. Since we're adding noise on the magnitude of k over epsilon, the error we get per query also is something like k over epsilon. So the more queries we answer, the more noise we have. It's a nice use of composition. Here, the error depends linearly on the number of queries that we answer. So for example, if we want to have at most root n error, that's error that we like in statistics, is sort of the error we get from sampling effects. If that's all we're willing to add, then we can answer up to about root n queries, where n is the data set size. So perhaps if you're collecting data for a medical study of a rare condition and you don't have a lot of participants, root n maybe is not enough. But if you have a huge data, like an internet scale data set, root n already gives you quite a lot of queries that you can answer. Okay, so that's basic composition. It tells us that we can answer, if we do k analyses, the epsilons simply add up, and we get epsilon 0 times k differential privacy. And the next thing I want to talk about is advanced composition, sort of more refined or more complete understanding that we arrived at a few years ago, which tells us that, in fact, this is a very pessimistic view of what's happening when we compose analyses. In fact, when you look inside what's actually happening when you compose differentially private algorithms, something a lot better is happening. And in fact, you can say, and this is, I mean, I'm really, really lying here, and I'll tell you what the real bounds are in the next slide. But at a high level, what you can say is that the privacy loss degrades as epsilon 0 squared times k. So think about epsilon 0 as a very small constant, or think of it as 1 over root k. You're doing much better here. We're doing much better here than we were under the basic analysis. Okay. So in fact, to make it a little bit messier, but also to be a little more honest, this is what we can show. If we take k algorithms, each of which is epsilon 0 differentially private, when we look at the global privacy loss under composition, the way it scales is something like root k times epsilon 0. Compare that with a basic composition where we had k times epsilon 0. Here we're doing a lot better. We have this log that I'll talk about in a minute. We have root k times epsilon 0 plus k times epsilon 0 squared. For most choices of epsilon, this will be the dominant term. So we're doing, epsilon 0 is much smaller than 1, so we're doing much better. And this is almost always true. It's not always true, unfortunately. There's some probability of a privacy error, of things going wrong. So with some probability, with some delta probability, things do go wrong. But if we can have a very small probability here, and still in the cumulative total privacy loss, all that we'll pay is the square root of the log of that error probability. So this does let us do, if we're willing to live with even a cryptographically small probability of error, we can still do a lot better than we could with basic composition. And this is the theorem I want to tell you a little bit about. Of course, now I've suddenly dropped this bombshell that there's a probability of error. Things can go disastrously wrong. So I want to talk a little bit more about that and then give you the intuition behind why this better theorem holds. Why are things actually better than they looked at first glance? So in order to understand this error probability, I'll say in advance the error probability is only over the coins that the differentially private algorithm is tossing. And these coins let us think about privacy loss, the privacy loss of the algorithm. And this privacy loss is actually a random variable. So differential privacy lets us quantify and reason about privacy loss. And the way we reason about it is the following way. We fix our adjacent data sets. So D is the real data set with my data in it, and D prime, my data has been completely erased and taken out. And now we run the algorithm, the mechanism, on the data set D, and out comes an outcome, right? It publishes some outcome, so it tells us what the correlation between smoking and cancer is. The privacy loss for that particular outcome that was generated is just the log ratio of the probabilities of that outcome when the algorithm was run on my data set and when, on the real data set, and when it was run without my data. Okay, so this ratio of probabilities is the ratio that we know and love from the definition of differential privacy, and we're just taking its log. So notice this is a random variable because this outcome, the algorithm is randomized, so this outcome that was drawn, was drawn randomly. It's in a probability space. And privacy loss lets us attach a number to this outcome. It tells us how privacy disclosive is this particular outcome that we got. And looking at this number when we run the algorithm, outcome's an outcome, and that outcome is associated with a certain privacy loss. And in fact, this loss can be positive. That means that we've lost some privacy. It can also be negative. That maybe is a little less intuitive. And it can be infinite. For example, if the algorithm tossed some coins and decided to just release my information, that's what we call infinite privacy loss. So to understand why, for example, privacy loss can be negative, let's look at an example. And let's suppose that we're running an analysis that counts the number of people that are above 6 feet tall. Okay? So when I'm in the data set, the number is 20, that's in D, and when I'm not, the number is 19, D prime. And we're adding Laplace noise, so if we look at the probability distribution function of the algorithm on these two data sets, here we see adding Laplace noise to the number 19, and here we're adding Laplace noise to the number 20. So we run the algorithm on the real data set, here on the right. Out comes some answer for the number of people who are above 6 feet tall. And that answer, with probability at least a half, it's going to be out here, and it's going to sort of indicate, it's going to be above 20, and it's going to indicate that I'm probably in the data set, or it's going to increase the confidence that I was in the data set. And that's because the outcomes here to the right are more likely when I'm in the data set than when I'm not in the data set. So the ratio is bigger than 1, and its log is positive. But on the other hand, suppose we ran the algorithm, and for some reason it tossed a really large, the noise came out to be a really large negative number. So the outcome came out to be somewhere here. I suppose the noise was -5 or so. Now we're getting an outcome that is more likely, even though we ran the algorithm on the data set that I was in, we're getting an outcome that would be more likely if I wasn't in the data set. So to an observer looking at this outcome, it increases the observer's confidence that I wasn't in the data set, or decreases confidence that I was. So here the probability according to D prime is larger than the probability according to D. The log is less than 1. The privacy loss is negative. I've actually gained some privacy. It's an intuitive way of thinking about it. And because privacy loss can be negative, and in fact, you see here, it can be negative with probability that's close to a half. So long as I'm to the left of this intersection point of the curve, so long as the outcome is to the left of the intersection point, the loss will be negative. I'll gain some privacy, and that's what powers the advanced composition. That's sort of the insight. We're going to leverage that in order to get more powerful composition guarantees. Okay? It happens when we run a single analysis, this happens with probability close to a half. When we run many analyses, it's going to happen a lot of the time, and it's going to let us show better bounds on privacy. So privacy loss, as we've said now, it's a random variable. It's a real valued random variable. Particular, it has a mean. We can think about it. It has a variance. We can look at this random variable. We can study it. We can learn all sorts of interesting information about it. And that's what the study of composition essentially is doing. When we think about this, when we recast the definition of differential privacy that Cynthia told us about, really what differential privacy is telling us is that always, for any outcome that we draw, that is drawn by the algorithm, the magnitude of the privacy loss is bounded by epsilon. Okay, this ratio is bounded by e to the epsilon. Its log is bounded by epsilon. Now, there's a relaxation that we will talk about and that's discussed, that's studied a lot in the literature, that's called epsilon delta differential privacy. I'm cheating a little bit. I'm not giving you the real definition, but I'm giving you a definition that's close to it. And basically what that's saying is that with all but delta probability over the coin tosses, with all but some small delta probability of disaster, we're fine. The privacy loss is bounded by epsilon. So if this delta is cryptographically small, if it's smaller than the chance that your crypto scheme is going to be broken, if it's smaller, I mean, I won't say it's smaller than the chance of a certain candidate being elected president, but it's smaller than the chance of an asteroid flying into the Earth, then this seems fine. Okay? We can have a tiny probability of a giant error. That's the kind of thing we're used to thinking about as cryptographers. And with this in mind, now we can understand what I mean when I say with all but this delta G probability, we have a bound on the global epsilon when we compose K algorithms. And notice here that this actually holds for any error probability that you want. So you can choose your error probability, your probability of a privacy error, and for any error probability you're willing to tolerate, you have a guarantee on the cumulative privacy loss over the K algorithms. So why is this important? Well, we said composition is a core issue in the study of differential privacy. The minute we have better composition guarantees, we can build better differentially private algorithms. Okay? We can use maybe more subroutines in order to get a better accuracy for our analysis, or we can use the same number of subroutines and get a better privacy guarantee for the algorithm. So really that's important. When we go back to the question of answering queries, just answering statistical queries, low sensitivity queries, using Laplace noise, this improved composition theorem already lets us answer n queries, where n is the data set size, with error that scales roughly like root n. Okay, so now instead of only being able to answer root n queries as we were before, we're able to answer as many queries as the data set size just using independent Laplace noise. And I'll note that this now matches the fundamental law of information. I think you said retrieval, right, Cynthia?
I said reconstruction.
Okay. So recovery. So reconstruction, recovery. So we know from the work of Dinur and Nissim that we must have error at least root n. We're almost matching that. Using advanced composition up to this log of the error probability. And in fact, it's used all over the place. It's also used in results that use coordinated noise in order to answer large number of queries. And their advanced composition shows us that we can answer huge number of queries, and the error only needs to scale as log the number of queries that we're answering. Okay, so how do we actually prove advanced composition? I won't dwell on it for too long, but I want to tell you a little bit of the intuition. So I told you that the minute we think about privacy loss as a random variable, we can study it. It has a mean, it has variance, it has higher moments. And one thing that's really interesting about it is its expectation. So if we look at the privacy loss of any epsilon differentially private algorithm, we know that the ratio, the privacy loss is bounded by epsilon. It's no worse than epsilon. But in fact, the expectation is always going to be much better than this worst case bound because we have negative privacy losses. And what we can show is that the expected privacy loss for any epsilon differentially private algorithm is at most epsilon squared. Most about epsilon squared. So now we have this random variable privacy loss. It has a small expectation, only epsilon squared. And we know that its absolute magnitude, since we have differential privacy, the absolute magnitude is always bounded by epsilon. And the way we show advanced composition is we model cumulative loss from multiple analyses, from multiple algorithms, as a martingale. Now we have these random variables. They have bounded expectation and bounded total magnitude. We can use, for example, a Zuma's inequality to show that the probability of a large loss is bounded, is tightly bounded, is very small. That's what powers the advanced composition theorem. So I have a picture rather than dwelling on it, and you can see this is the privacy loss. It's sort of bouncing around the origin. It can go up, it can go down as you run more analyses, but in the end, we know that it will settle not too far from the origin. You will go about root k times epsilon steps away from your expected total loss. For all of this, I assume that all of the algorithms we were running were epsilon differentially private. There's also composition for epsilon delta. If you're starting with epsilon delta algorithms to begin with, ones that have small probabilities of error, you can compose them, and you'll still get the same sort of global epsilon for your total analysis. The global probability of error is now the deltas basically sum up and get added to this probability that your random walk is too large, to this error probability that we had before in the bound on epsilon. Okay, so we know about basic composition. We've talked about advanced composition. That gives us this epsilon squared understanding. And for the rest of the talk, what I want to tell you about is a more refined understanding. We've been going even beyond this bound to really understand what's happening with privacy loss, to really understanding how composition works. So the first two works that I want to tell you about actually ask, well, this is a very nice bound, but can we do better? Can we do, what's the best that we could hope to do? And we actually have an understanding now of tight bounds. We understand exactly what's possible and not possible to show for composition of differential privacy. And then we have tight bounds, but we still want to say more. So I'll explain to you, even though we have tight bounds, what more we can say. But starting with that, with the question of tight bounds, so that's a very natural question to ask. First of all, given a collection of algorithms, of mechanisms, that have certain privacy guarantees, what is the best global epsilon and global delta that we can show for the composed algorithm that runs all of these? Here by best I mean over all events. What's the best bound that we can show? So we had basic composition that told us one bound. That turned out to be far from optimal. Then we had advanced composition that gave us a better bound. But really, what is the best that we can show for a given collection of algorithms? And then an even more general question, if we don't even know this, if we don't want to be concerned with the particular algorithms that we're given, if we want an automatic theorem that will work for any algorithms that we get, if we're given certain bounds on the privacy of each individual algorithm, so we know that the first algorithm has a certain epsilon, the second algorithm has a certain epsilon, et cetera, what are the best global epsilon and delta that we can show? Where here by best I mean over all algorithms, all mechanisms that satisfy these given privacy guarantees. So we're guaranteed that the first mechanism satisfies epsilon 1, delta 1 differential privacy, but we're not guaranteed anything else. What we want to know is the best over all possible mechanisms of the privacy loss, the privacy bounds that we can claim. So really, that would let us sort of automatically, we're talking about making differential privacy programmable, that would let us put together automatically any building blocks. All you would have to specify about your algorithm is its epsilon and its delta, and then we would put it together with other algorithms whose epsilons and deltas are specified, and we'd automatically know what their privacy guarantees are, what the combined privacy guarantee is. So that's going to be our goal. For the homogeneous, oh my God, I'm blanking now on the name, Kairouz O and Viswath, I believe, analyze this for the homogeneous case, where all of the epsilons are the same for all the k algorithms and all the deltas are the same. And they actually were able to, amazingly, they were able to show tight bounds. They were able to give a succinct expression that tells you exactly what happens in the worst case and is tight. Okay? So it's true for all algorithms, and there are algorithms for which you can't show anything better. And this showed about a 30, depending on your epsilons and your deltas, this is a 30 to 50% improvement over the advanced composition theorem. So the advanced composition theorem is asymptotically tight, but still when we're composing differentially private algorithms, we want to get tight bounds. We don't want to pay large constant factors, that's important, and they were able to show a large improvement over the original advanced composition theorem. Then the heterogeneous case was analyzed by Murtagh and Vadhan, For general epsilons and deltas, when they don't, not all mechanisms have to have the same bounds, they again were able to show this time a more complicated expression for what a complicated tight expression for what the total privacy loss is. Unfortunately, it's a complicated expression, and it's not just complicated in terms of looking at it, it's also computationally intensive to actually compute what the bound is. So given a collection of mechanisms, we know we have an answer in terms of what the tight total privacy loss is, but given a collection of mechanisms, it would take exponential time to compute what the actual privacy loss is. And for the complexity theorists in the audience, what they actually showed is that computing the total global epsilon for the privacy loss is Sharpe complete. So it's even harder than an NP complete problem, is a way of thinking. We think it's harder than an NP complete problem. That's a way of thinking of it. Really, we don't expect to be able to do this using less than exponential in k time. So we have some existential result. We know that we can characterize the cumulative loss, but we have no way of actually specifying what it is in the real world, of actually computing what it is. That's a little bit of a disheartening state of affairs. They did show an approximation algorithm. So they showed an additive approximation algorithm given the bounds of the individual algorithms for computing the total privacy loss. So I do think it's worth pausing on to think that I thought this was startling, that we could get an actual completely tight understanding of how differential privacy works under composition, what the composition bounds are. Unfortunately, we have some challenges. First of all, computational complexity. Also, our understanding really is worst case. And when we look at the particular algorithms that we want to run, they're not worst case algorithms. We can hope to do better. And that's what sort of lies at the heart of the alternative approach that I want to tell you about in the time that I have left. So given this state of affairs, what are some goals that we should have for composition? First, of course, we want to be able to reason about it efficiently in polynomial time, to really have our hands on what's happening with our privacy losses. And also, we want to get better bounds. We want to have smaller errors. We don't necessarily want to think in the sort of worst case about all the possible algorithms that might satisfy a certain epsilon delta guarantee. And in particular, one thing that we should really focus on, or that really where there are stark differences between different algorithms, is in the delta guarantee. And we've taken to sort of distinguishing between two different deltas that we can have that are very, very different. The first is what we call the delta of death and destruction. Okay, that's a really bad delta, as you might guess from the name. And those are algorithms where really it's true that with probability delta, all privacy is lost. Okay, so what's an example of such an algorithm? It's an algorithm that looks at the data set and with probability delta just releases all of my information, my medical history, all of my tax reports. That's a death and destruction delta. There's no recovering from that. Things are really bad with probability delta. That was a made-up example, but there are deltas of this type that come up in very nice algorithms in the literature. The proposed test release framework of Dwork and Ley is one such example. So there are these bad deltas. We need to think about them, but they're not, I wouldn't say they're rare, but they're often not the deltas that we see. The deltas that we often see are deltas that come due to concentration bounds. Okay? Really, what we have is we have a privacy loss that has some really small expectation. It's concentrated around its expectation, but with some probability it's going to fall beyond, some big bounds that we impose on it. So in that case, what we do is we specify some big epsilon, much bigger than the expectation, and we say, well, we have a small expectation, we're concentrated around it, things can go wrong, but you're only going to be far from the expectation with delta probability. And when we specify an epsilon, when we talk about an epsilon delta algorithm of that type, really we're being very conservative. We're specifying an epsilon that's much larger than what we expect to see in real life. And we're paying the price for it, right? Once we've specified that that's our epsilon and delta, it goes into an automatic composition theorem. No one knows what's happening inside the algorithm, and we lose a lot. We lose a lot of privacy, or we lose a lot of accuracy. Okay? And this happens all the time. Okay? So some of the canonical mechanisms in the differential privacy literature, if you're adding Gaussian noise, you have an epsilon delta privacy guarantee, but that's a delta of concentration. If you're using the advanced composition theorem, which hopefully you're doing a lot, the delta you get there is something you get from an Azuma inequality, so that's also a delta of concentration. And that motivates this notion of concentrated differential privacy in work with Cynthia, and also building on that, there's been some very nice work of Ban and Steinke that further explores that notion. So we have our privacy loss, recall we have our privacy loss random variable. What concentrated differential privacy does, it's a relaxation of differential privacy. And all it wants is it asks that this privacy loss random variable have a small mean and be tightly concentrated around its mean. So now the privacy guarantee is quantified by two parameters, mu, which is the expectation, and tau squared, which is, think of it as the variance for now. And what we ask is that the privacy loss has expectation bounded by mu, and is tightly concentrated around this expectation. Intuitively, the concentration should be no worse than that of a normal random variable. Okay, so it's sort of like a Gaussian or a normal distribution, very tightly concentrated around its mean with standard tau, with variance, tau squared. That was our approach in the work with Cynthia. Ban and Steinke had an alternative where they also talk about they want the random variable to have small expectation and concentration, but the way they formalize it is using Renyi divergences, and I won't talk about it. I'll tell you a little bit about some nice things they're able to achieve using that, but I'll focus on this sort of more intuitive, to me at least, formalization where the concentration sort of looks like a Gaussian. Okay? So looking at it pictorially, I have a graph. So if we look, we can now think about the cumulative distribution function of the privacy loss random variable. If we have an epsilon 0, an epsilon differentially private algorithm, we know that the privacy loss is always between -1 and 1, for example, if we have an epsilon of 1. If we have an epsilon delta differentially private algorithm, we know that with all but some small probability, here the probability is 0.1, the loss lies here between -1 and 1. But with that probability, the loss can be infinite. With the delta probability, the loss can be infinite. It can be doom and destruction. Concentrated differential privacy, when we look at the privacy loss random variable, it just looks more or less like a normal distribution. It's usually going to be between -1 and 1. It might go all the way up to 2 with some smaller probability. It might go up to 3 with some even smaller vanishing probability. It has a small expectation, and it's concentrated around its expectation. It can go out further, but only with small probability. Okay. Formally, the way we define this is using the theory of sub-Gaussian random variables. Basically, for the talk today, you can keep your intuition that the privacy loss is sort of like a Gaussian, is concentrated around its expectation like a Gaussian random variable. And this formalization, it's a relaxation of differential privacy. We're giving some probability of larger and larger, some smaller and smaller probabilities of larger and larger privacy losses, but it maintains the important advantages of differential privacy. In particular, for composition, it composes automatically and efficiently and optimally. Okay, so really, this is a definition motivated by and geared towards composition. When you compose, all that happens is that the expectations and the tau squared parameter simply add up. Okay? It also handles auxiliary data. It's future-proof similarly to standard differential privacy. In terms of comparing it to the notions that we had before, we talk about a single analysis or a single study. We have weaker guarantees. Okay, so comparing it, we do have these smaller and smaller probabilities of privacy losses being larger and larger. So I think it's an interesting question. I personally haven't wrapped my head quite around whether I would advocate for concentrated differential privacy as a standalone definition of privacy, because we do have these probabilities of larger privacy errors, and it's sort of a social question. Are we willing to live with that? Is that a reasonable guarantee to give to individuals? So we can debate that. What we don't need to debate is that if we're talking about many analyses, if we're in a situation where there's composition, and as I've argued before, there's always composition. Composition is just a fact of life. Then the privacy behavior is roughly identical to what you get even for pure differential privacy. Okay, because under composition, really what happens, we have this advanced composition theorem, things are going into something, things are converging to something that looks like a normal distribution anyway. Okay, so over many studies, if we're in a setting with composition, concentrated differential privacy is no worse than pure differential privacy. In terms of accuracy, if we want to answer, go back to this question of answering k queries, we saw that for basic differential privacy, we need noise on the order of k using basic composition. For relaxed, for epsilon delta differential privacy, we could get the noise down to root k for answering k queries, but we had to pay this log 1 over delta factor. And now if we're going with CDP, we can simply get the noise down to root k. Going back to the fundamental law of information reconstruction, we can really get tightly matching bounds to to the best possible under any reasonable notion of privacy. These are just plots of what would happen under composition of many analyses. So you can see that all the different definitions are converging. In fact, epsilon delta differential privacy is a little bit worse because once you have a delta, it could be a delta of doom and destruction. You can never get rid of it. So those deltas add up when you compose. This is a comparison of noise magnitudes. So you can see pictorially that concentrated differential privacy lets you do significantly better than the other notions. Here the black curve is just the, sort of the noise you would have by sampling effects anyway. So we're getting pretty close to the noise. This is an example with 200 individuals. 2/3 of them have a condition, 1/3 don't. The black curve is the noise you would get by sampling effects. We're getting pretty close to that. So in terms of advantages, we have tight, efficient composition bounds. We can have sharper analyses for private algorithms. Group privacy that Cynthia talked about, we also concentrated differential privacy works very nicely for group privacy, more nicely than epsilon delta differential privacy. So if you have a group of size g, you just have a g squared degradation in the expectation and in the concentration parameter. That's sort of the optimal you would expect. We had some little o of 1 terms in our group guarantees, but this was tightened by Bahn and Steinke in their work. They give a very nice group privacy bound. And then I think it's already, concentrated differential privacy is already finding applications. This way of reasoning about privacy loss under composition plays a role in a private deep learning algorithm due to Abadi et al. It's also found an application in release of energy use statistics by a California public utility company. Some open questions and challenges, and then I'll wrap up. So one challenge is post-processing. So what happens under post-processing of the results of the analysis? What turns out to be the case with concentrated differential privacy, the expectation can't increase, the expected loss can't increase, but if it decreases, then suddenly your concentration parameter can increase by a little bit, can degrade by a little bit. So alternative formalizations don't suffer from this, don't have this problem, and do give us guarantees under post-processing, both the original definition, if you tweak it, and certainly the Bahn and Steinke formalization is robust to post-processing. We're still trying to understand subsampling. So differential privacy has this really nice property that if you start with a data set of information, a data set of data about individuals, and you subsample, you choose random individuals from that data set, and then you run a differentially private algorithm, you get the privacy of the differentially private algorithm is amplified. Okay, it's sort of, you get an even better privacy parameter, sort of reduced accordingly, proportionally to the fraction of individuals you sampled. For concentrated differential privacy, this isn't the case. So we can't use subsampling as is with concentrated differential privacy. We can't get the similar kind of privacy amplification. And I think this motivates our continuing search for what we really want to do is we want to understand composition. We want to understand privacy loss of differentially private algorithms. Ideally, what I hope we can get to is one framework that will cover everything that we want, that will really let us automatically, sort of a programmable way, put together different privacy-preserving algorithms and really understand what's happening to their cumulative privacy loss. We're almost there. We still have a little bit of work to do on things like subsampling. Okay, so to end and sum up, composition is a core issue in the study of privacy. Hopefully, I motivated that. We have a more and more refined understanding all the way up to completely tight, no constant factors, nothing, completely tight composition guarantees for differential privacy. And now we have these sort of more refined understandings and frameworks to work with in understanding privacy loss. And I think the grand challenge for this type of research is what happens when K gets really large. Okay, so really we're running on the internet and K isn't equal to 100 or 1,000, but there are millions of analyses and our data are being analyzed constantly. For example, on the internet, what can we do? And one thing I'm becoming really interesting is if we talk about programmability, coming up with a library of templates for dealing with, well, if not all of the results of all of the algorithms are released, but rather we're running a bunch of algorithms and then doing some sort of post-processing on them, we're putting them together in an interesting way, what kinds of privacy guarantees can we give that are better than sort of just worst-case composition, what you would get if you did release all of the outputs of all of the algorithms? And we have some examples in the literature. For example, if you just took them, if you run many algorithms and take the max, certain things happen. We have things like a sparse vector analysis that's, I think, is also a template you could think of for composing where you do much better than the worst case. But it would be nice to have a library of these kinds of ways of programming together differentially private algorithms. And then the other thing is, if we're really talking about composition at internet scale, can we leverage just the scale of data, the amount of uncertainty that an adversary might have about data that isn't just my own, but other individuals in the data set? It's been a long-standing challenge. It would be nice to find a robust way of arguing about that and getting better bounds. That's all I wanted to say, so thank you for listening.